yesterday we finished up talking about the transformations. At the end, we talked about how if you're going to do transformations, the particular order makes sense to do H, S, R, V, okay? And H stands for horizontal shift, okay? S stood for stretch or shrink, R stood for reflections, and then V stood for vertical shift, okay? And really the only thing that is important is that we do this vertical shift last, okay? But the idea here is, you know, if I have like a function, let's say f of x equals, let's say the opposite of, let's just say like x plus 3 squared plus 1. Hey, what's up?
Is that not working?
No, it like exploded yesterday.
Oh, snap! All right.
All right. So if I'm looking at this, guys, and I wanted you to graph that, okay? I don't want you to create a table and say, okay, x and f of x, and try to figure that out, okay? What I want you to know is, okay, well, I know on the parent function maybe the point 2, 4 exists, right? Okay. And I'm going to run through these real quick and say, okay, if 2, 4 exists, 3, 9 exists on my parent function, take and do, is there a horizontal translation? Is there a shift left or right? Yeah, 3 left. So I'm going to take this thing here, I'm going to make it go 3 left. So it'll be -1, 4, right? This will be 0, 9. Okay. Is there a stretch? No, there's not, right? Is there a reflection? Yeah, and the reflection is across what axes? X. So that's going to make my y's negative, right? Okay. And then there's a vertical shift of 1, so it becomes -1, -3, 0, -8, and now I've got 2 points that show up on that curve. Does that make sense? Yeah. So it should be a tool that allows us to take our parent function points, and you know the way I think about it visually is if I've got, you know, the point 2, 4, okay, how do I grab that point through the transformations and move it around to where it needs to go on to the new graph that I'm interested in? Okay, so that's kind of the benefit of these procedures that we've been talking about. And that's something in mathematics that I think gets overlooked a lot, is we learn how to do certain things, but we never really maybe spend time on talking about, you know, how does that really benefit me? I know how to do it, but how does that help me in regards to everything else? Okay, and remember what math is. A lot of people think math is all about calculations, right? Math is a system of defined rules and procedures that actually allow us or are intending us to be able to do things without calculations, to avoid calculations. Does that make sense? Okay. I talked to my algebra class the other day, and we were talking about, you know, what was the first thing you guys learned how to do in school? Count, right? Okay. So let's say I've got, you know, 6 whatevers there, okay? I guess I've got 7. I didn't learn how to count. So I got 7 of these. And if I want to know how many I had, first thing in, you know, preschool, I had to go 1, 2, 3, 4, 5, 6, 7, right? Well, whatever these are, let's say somebody steals 2 of them. Before I learned how to do subtraction, I had to go, to know how many I had left, I had to go 1, 2, 3, 4, 5. Now I know I have 5 left, right? But if I know subtraction, I started with 7, somebody took away 2, I now have 5, right? Is that process a quicker way of counting what I have left? Right? Okay. Everything that we do essentially can be worked back to that. Okay. So everything that we do in mathematics, all the rules that we have developed in mathematics, is intended to alleviate having to do calculations, okay, or alleviate having to do counting, okay. One of the tools that we like to use to help with graphing is determining whether a function has a particular type of symmetry. Okay, symmetry. Does anybody not understand what symmetry is? Do I need to explain what that is? Okay, so symmetry we know has, for instance, let's take like this. Let's say we take that thing right there, okay, and I reflect it across that line there, okay. I don't know what this thingy here is doing. Do we have symmetry? We have y-axis symmetry, right?
Yeah.
Okay. Y-axis symmetry, because if I fold it on the y-axis, every point on there is going to match up to a corresponding point on that one. Okay. Now, if I take that one and reflect that one across that line, okay, are these two symmetric in regards to the x-axis, right? Okay. Now, here's my question. Are the original and, oh, that's not the one. Let's make this one blue. Make that one. Let's go back to black. All right, so is there a relationship between the red one and the blue one? Okay, so we have, if I have a point at 0, 0, and I take this red one and rotate it around point A, isn't that gonna let me do it? It might not let me do it because it's a freehand curve. All right. If we, and we'll see this in a little bit, but any point that we put on here, let me put a point like right there, okay? And I rotate that point 180 degrees. Why won't that work? Oh, that's why, yeah. Okay, so it's referencing this parametric curve. I don't want to, that's a good call. So let's put B here. There we go. So let's do, we can make this one then go around there. So there we go. So take that red one and rotate it 180 degrees. It matches up completely with that blue one, right? Okay. So what we've got there is you can see maybe some relationships with stuff that we've talked about in geometry. Okay. Any point that's on there, so point B prime is going to go and corresponds traveling 180 degrees to B prime. But there is symmetry there. Okay. And it's called symmetry with respect to the origin. Okay. If you look at point B and B prime, what is the relationship between them? Yeah, so if you remember back to geometry, we had a rule that says if I do a rotation around the origin of 180 degrees of a point A comma B, it turns into the point negative A, negative B, right? Okay. Some of what we talked about in geometry is going to come back to being part of our discussion today. Okay, and it has to do with these, essentially these ordered pairs. Okay, what you're going to find out, and I prefer to do this because I had you all in geometry. Okay, is make connections back to that. Okay, because I think if you understood geometry, it's going to allow you to understand algebra a lot better. If you understand algebra, it's going to allow you to understand your geometry a lot better. There's a lot of times, especially the graphical aspect of things. Okay. Actually, the Cartesian plane, the XY axis, is the bridge between those two branches of mathematics. Okay, and that's really what we're focused on here when we talk about these transformations. If we want to take a function, so I'm going to talk about like this function right here, x cubed. Okay, there's a lot of points on there, and I'm just going to look at this branch right here, this right hand side. Okay, let's see if I can actually change part of, there we go. I'm going to look at the blue section. Okay, the blue section, I know some ordered pairs off there of 1, 1, 2, 8, 3, 27, so forth, right? Okay, it would be really nice if there was a relationship that allowed me to say, okay, if I know the points that are off that one, okay, off that branch, can I take and rotate that branch and get points that are on the green? Does that make sense? Okay. So the idea is if I look at, the point 2, 8, which is point E, okay, and I start to rotate this thing, and I'm actually going to, let's see here, I need to rotate E as well, so let's see here. Okay, so E prime right now, if I look at its object properties and go look at its ordered pair, so it's 2, 8. Okay, when I rotate, okay, and it comes down here, what's the ordered pair there? It's now -2, -8, right? Okay, which is a relationship between these two. So if I know I've got a cubic here that has this symmetry, so I know that x cubed has symmetry about the origin, I can use that fact to really help me graph this red part. So basically what these symmetries that we're going to talk about today are going to allow you to cut your work in half, okay, in regards to graphing, or maybe cut your memorization of parent function points in half, and then know, okay, these functions are even or they're odd, and that tells me then how to find the other half of points to plot. Does that make sense? Okay. So the first type of function I want to talk about is called an even function. Now this has nothing to do, I don't want you to think, oh, that means I have like even exponents or something like that. That's not what we're talking about here, okay? Even refers to the type of symmetry it has. An even function is symmetric with respect to the y-axis, okay? And what that means to us essentially is if I take a function like x squared, which I think we all know that x squared has a axis of symmetry being the y-axis, right? Okay. All this is saying to me is that if I take this point B that is on my curve here, where'd B go? There we go. If I take B, which is on one branch of my parabola, okay, and it's on the right-hand side of where I think I have my symmetry, if I were to reflect it, and its reflection lands on the other side of my curve, okay, does that kind of make sense to everybody? We see that reflection happening, okay? And I trace out my entire curve, then I have y-axis symmetry. Does that make sense? Where if I do something like this, let's say I have like x squared plus like 2x. Now look at that graph. Okay. Now if I take that point B and start moving it, do I trace out the green curve? Is it a direct overlap? No, right? Okay. So this curve here would not have y-axis symmetry. Okay, it's got symmetry, but it's through the axes, like right, or not the axes, but the line of symmetry is right here. Okay, through -1. Questions on that? Let's look at this real quick. Let's go back to just x squared. Give me a point that's on x squared. 2, 4. Okay, so 2, 4 is on x squared. If we look at 2, 4, okay, its reflection is -2, 4, correct? Okay. Now 2 is an x coordinate, right? 4 is a y coordinate, but this thing's a function, and we know if it's a function that the y coordinate is defined as f of x, right? So I'm going to say 4 is f of x. Okay. What would be the relationship over here? Using that ordered pair of x comma f of x, what would you call this over here? Opposite of x comma f of x. Because they're the same, right? Okay, this is the opposite of that 2, and these 4s are the same, so that allows us to make this argument there and that argument there, right? So does that happen with all points? If I go to like 3, 9, 3, 9 would be about right there. Do I get -3, 9? Or we get x comma f of x and x, or opposite of x comma f of x, right? Okay. So what we're seeing here, and actually what we would be doing to get this 4 right here, I actually inputted a negative x. Does that make sense? So if this would have been negative x, this would have actually been f of negative x inputted there. Does that make sense? But what is the relationship of that 4 there and that 4 there? They're the same number, right? So what's that tell me about that and that? They have to be the same. So f of the opposite of x has to be the same as f of x. And that's what's going on here. If I evaluate x squared at negative x, okay, or -2, I will get the same thing I get when I evaluate f of x at x or at +2. Does that make sense? I'll get the same 4 back. So that is the algebraic tool that we're going to use to prove whether a function has y-axis symmetry. Okay? We could, I mean, you know, I looked at 2, 4, and that can convince me, yeah, that worked for 2, 4, but then I have to check, does it work for 3, 9, and check those. Does it work for, 1, 1, check those. Does it work for 4, 16, check those. And then I'd have an infinite number of points in between that I have to check, right? So going back to geometry, when we prove something, the geometric proof was intended, the way it was structured is so that we prove all situations to be true at once. Okay, eliminate the possibility that maybe I've shown an infinite number of ways, but there's this one counterexample. Okay, this here is that idea. Okay, this is going to allow me to check all of these x and y values instantaneously. Okay, and not have to go through and do each specific ordered pair and see if its reflection happens or occurs. So we're going to do a couple examples here with an even function. So if I have an even function, the parent function x squared is even. So we'll start with that one. It's pretty easy. I know I've got the work here, but if I start f of x equals x squared, the question is going to be, eventually. Is that even, odd, or neither? And what we need to do is we need to check, well, does f of x, does it equal f of the opposite of x? So I've already got f of x. That's what I started with. Now I got to figure out what is f of the opposite of x. Okay? Now think about what we're doing here. This is going back to section 2.1.2.2. It's going back to algebra 1 function notation. If I've got negative x, okay, it's like if I had like f of 2, right? If I had f of 2, I'd be plugging in 2 for that x, right? If I had f of like negative 3, I'd be plugging in negative 3 for that x. Now you're plugging in negative x. So for this x right here, I'm going to plug in negative x. And once I do that, I have to evaluate. So what's negative x times negative x? X squared. And now here's the question. What do you recognize about that quantity there and that quantity there? They're the same. So what's that tell you about f of x and f of opposite of x? They're the same. So what's that tell me about this function? It's even, right? And because I know now x squared is even, the benefit of knowing that is that if I want to graph it, I now only need maybe 0, 0, 1, 1, 2, 4. Because now if it's even, I automatically know negative 1, 1, negative 2, 4 also show up. Does that make sense?
Yes, it does.
Okay. If it's an even function and a, b is on your original function or on one part of your function, then it implies that negative a, b is also going to be there. Okay. So that maybe for x squared, it doesn't save us time to determine it as an even function and then say, okay, well, that cuts down my number of ordered pairs that I have to plot because I know this relationship. But if I give you a polynomial that has like x to the 6th in it or something like that, and maybe we've got 7 terms in that polynomial, it might be easier to determine if it's odd first and then grab a couple points off of it and allow that odd relationship or maybe the even relationship to generate the other ordered pairs. Does that make sense? Okay. What if I take something like, let's say we've got f of x equals x squared plus 3x minus 7. And I ask you, is that even, odd, or neither? Okay, and right now let's just see if it's even. So we're going to figure out what f of negative x would look like, right? Because the rule again is that right there. We got to check that. So I'm going to go everywhere I see an x in my f of x, I'm going to replace it with negative x. And I'm going to evaluate. So what's negative x squared? X squared. Okay. What's 3 times negative x? Negative 3x. And then I have my minus 7, right? Are these things the same? No. And remember, this is what generates my y values, right? Okay. So they're not the same. So then that and that are not the same. So we have shown that f of x does not equal f of negative x. So this is not even, right?
Right.
Okay. What's that mean then?
Odd or neither.
Okay, so it doesn't, when something is not even, it does not automatically mean it's odd. Does that make sense?
Neither also.
Okay, so it could be neither still. All right, so just make sure that we understand that idea. So let's come down, let's actually talk about the odd relationship. Okay. If we have a function that is odd, that's going back to the idea that we have symmetry across the origin. So let's look at, let's kind of play that same game that we were playing with the last one. So let's say, I'm going to zoom on this a little bit better. All right, so we have the point 2, 8 on x cubed, right?
Right.
Okay, so 2, 8 there, And down here, then we have -2, -8. We okay with that?
Yeah.
Okay. This here, let's call that x comma f of x. Is that okay? Okay. At this point down here, x would be, if x was 2 here, what's it down here? -x. Okay. Then the y value that pairs with -x is actually f of -x, right? Does that make sense, everybody? Okay. Now, if I look at that number there and that number there, is 8 equal to -8? No. How can I make them equal, though? Do something easier than that. You said square. I would. Okay, something easier than that. Multiply 1 by negative, right? If I multiply that one by a negative, does it make them equal now? Okay, so let's do this. So instead of looking at the 8 and the -8, let's look at f of x and f of -x. F of x right now does not equal f of -x in this situation, right? Because one is 8 and one is -8. Well, how do I make them equal? Multiply one of them by a negative. I'm going to multiply, and this is just what every textbook does, I'll multiply that one by a negative. And now they would be equal. And there's our algebraic check to determine if a function has origin symmetry, or sometimes we refer to it as origin rotation or symmetry about the origin. There's a lot of different ways that we kind of communicate that. So we'll do an example of that. So x cubed is our kind of go-to to initially realize if a function is odd or not. That's the first one that we practice. So f of x is equal to x cubed. And remember the rule then is, does f of the opposite of x equal the opposite of f of x? Okay, so now neither of these use f of x, right? So when it was an even function, we were able to use f of x. But now we've got to actually determine what is the f of the opposite of x, and we've got to determine what is the opposite of f of x. Those are the two things that you have to do. Okay? So I'm going to find out the opposite of f of the opposite of x. I'm going to take my x to the third, and I'm going to do something like that, right? Okay? Now what does that yield? What does that give me? Negative x cubed. Okay? Now if I go the opposite of f of x, there's my opposite, and x cubed is my f of x, right? If I evaluate that, what's that give me? Opposite of x cubed. What do you recognize about the opposite of x cubed and opposite of x cubed? They're the same. So what's that tell me about those two things? They're the same. So this checks out. X cubed is odd. So what's that mean then? That means if I know 0, 0, I know 2, 8, maybe 1, 1, maybe 3, 27. If I know those are on my parent function, or I guess on the right branch of this function, then I also know, so those are the points, like a comma b, then if it's odd, negative a, negative b also exists. So I should have negative 2, negative 8, negative 1, negative 1, negative 3, negative 27. Does that make sense? You guys remember in Algebra 1 when you were taught like how to graph something quickly? Or I guess not, I don't want to say graph something quickly, but you guys learned how to, when you graphed a line, how many points did you need? You needed 2, right? And then the next thing you did is you graphed like y equals x squared. And if you still use that same approach, that I only need 2, do you get a good graph of x squared? No, okay? Knowing if a function is even or odd allows you, okay, to determine whether I only need a certain handful of points. And then it will allow you to generate that other. So if I just do x squared, and maybe I did just positive numbers like 0, 1, 2, and 3, and I got that, okay? Maybe we did that in Algebra 1 and then realized, oh, well, I'm not getting the whole graph. But now if I know it's even, now it automatically gives me the whole graph, right? Does that make sense? Yeah. Okay. Now, not all functions are going to have symmetries. Okay, so I want to come over here. We got some examples here at the bottom, and we're going to determine, are they even, odd, or neither? Okay, and it's important to understand that A lot of functions are neither. Okay. Say again. Yes. So here's the idea. In all of our rules, we've got the f of x equals f of negative x. Okay, that was the even rule, right?
Right.
Okay. We had f of negative x equals the opposite of f of x. That was the odd rule. Okay, if I list the things that we need to be able to determine even or odd, we're going to need f of x. Okay, because that's in that first rule, right? We're going to need f of negative x, because that's in that rule and it's in that rule. And you also need the opposite of f of x, right? So whenever I do one of these problems, and I think this is a good idea for you guys, whenever you do one of these problems, just go ahead and write those three things down. Because those are the three things that you're always going to need. And then try to determine which ones are the same, which ones are equal, if any of them are equal. So if I do f of x, obviously for us, that's x to the fifth plus x for this first example. Now I'm going to do f of negative x. So everywhere I see an x, you're going to replace it with what? Negative x. So whenever I replace, I'm going to do that with parentheses. And then evaluate that. So what's negative x to the fifth? Negative x to the fifth. Okay? Plus a negative x gives me minus x. Good. Okay? Then I'm going to do this one. We'll take x to the fifth and multiply it by negative. So I always put a negative, and then I put in parentheses my function f of x. And that just reminds me that I need to distribute that negative through. Gives me negative x to the fifth minus x, right? Right, so now I can look at those two. Those two are the ones that are equal, right? So if those are equal, that makes those two equal. And then just figure out which one of these rules up here makes the case for that. So that one's an odd. That kind of makes sense? Okay. We're going to jump down. I'll let you guys do B. B is going to end up being even. But and basically all you do is this again. But I want to check this last one with you. Okay, so I'm going to find h of x, I'm going to find h of negative x, and the opposite of h of x. So 2x minus x squared is h of x. The h of negative x would be 2, replace x with negative x. So what's 2 times negative x? Negative 2x, okay? And now you'll have, nope. Because this is positive, because order of operations, you got to do that first. So that's positive x squared, and then you got minus, so minus x squared. And now, if I want to multiply by a negative to 2x minus x squared, we're going to get negative 2x plus x squared. What do you recognize? That is different than that. It's different than that, right? So they're all different. So this one would be neither. So in that situation then, we don't have really a shortcut to help us with graphing. We just got to go back to our old techniques and work through those. Does that kind of make sense? Yes?
Why is x squared on the second one? Why is it x squared again?
Because here you could, because of the power 2 there. Order of operations says you got to evaluate that first. So negative x times negative x gives me positive x squared, right? And then you got minus a positive x squared. So that becomes negative.